Now let's talk about volumes. Volumes allow us to store data in voxels, which are basically 3D pixels. Imagine an image where you have this amount of pixels. Each pixel stores RGB information, and everything together will form an image, right? Instead of having a flat surface where the unit will be the pixel and each pixel stores a certain amount of information, we can have the red, the green, the blue channel, the alpha channel, depth channel, whatever channel you want. Imagine that volumes will be pretty much the same thing but in 3D. Okay, where instead of having a pixel as a unit, we will have a voxel. A voxel can store a lot of different types of information. The difference between the pixel, or the biggest difference between the pixel and the voxel, is that while the pixel will only have XY coordinates, the voxel will have an XYZ coordinate on a certain grid. The higher the voxel count, the higher the resolution of your volumes, but that will also require more memory. I have here another scene where we can test that out. So if you try to represent an object based on voxels, you'll get something like this. Let me turn on the shading. And here I have a controller that basically just controls the resolution of the volume, okay? These are all voxels of a grid. Where we don't have any information, they're void and empty, so we don't see them. If we have a low resolution voxel, it's really hard to grasp the details of the original object. But if we go way down to 0.02, for instance, then we start having a better idea of the details of this object compared to the original shape, which is this one. We have a voxel representation of the same object. Now, inside Houdini, you can work with standard Houdini volumes or open VDB volumes. A standard Houdini volume is essentially a box that is subdivided into a three-dimensional grid where each unit, each voxel, stores a certain type of information. Let's have a look at this. So this would be a Houdini volume. If we have a look with a bit more density, you'll see, so this is what we have. Each voxel is storing a value of density, and the areas that seem more dense are actually areas that are thicker, areas where we kind of overlaying a bigger number of voxels. That's why they seem more opaque. While, for instance, on this area, we don't have a lot of thickness, so it doesn't seem as opaque as here, but they all have the same density value. It's just that the number of voxels here is lower than the number of voxels that we see when we're looking on this direction. If I increase the voxel size to 0.1, you see we can't really distinguish much of the shape. If we want to have more resolution, we need to have a lower voxel unit to represent this. Let's go to 0.025 again. So as I mentioned, you have the standard volumes, the standard Houdini volumes, and you also have open VDB volumes that work inside Houdini. A VDB volume is pretty much the same thing, but it's more efficient because it only stores information on the voxels that aren't empty. As we saw here, I don't have any voxels here. But when you have a volume, these voxels around here still exist. They're just empty. Even though they're empty, they have a value of 0, but they're still there and that information is being saved. On a VDB, that information is not being saved. Even though we see this bounding box when we switch to VDB, actually what's happening is VDB is what's called a sparse volume. And if we have a look at the VDB using this VDB visualized tree, this is what's happening. So these are the areas where that the VDB is actually storing data. Everything else is just being discarded. Okay, even though we see this bounding box, we're not saving data on each voxel of this bounding box. We're only considering these smaller grids. Now, both types of volumes can represent scalar fields, which is what we're seeing here. So we call it a scalar field because each voxel is saving one float value, in this case, of density that goes from 0 to something. Next, you have a velocity field, and a velocity field will be pretty much the same thing, but instead of saving just a float number, it will be able to store a vector, and that will give us some velocity fields that we can use to displace and advect either particles or the density values or something like that. I'll show an example of a velocity field in a moment. Now, the other type of volume that you can have is an SDF, a signed distant field, which will represent a mesh and the distance to the surface of that mesh using either positive or negative values depending on whether the voxel is inside or outside the mesh. For instance, let's see here, this input here. So this is a standard volume SDF where we're generating an isosurface, and this value, what we're seeing here, is a representation of the voxels where the value is 0. If it's inside a mesh, you will have a positive value. If it's outside a mesh, you'll have a negative value. These will be different if you're using a standard volume or a VDB. VDB, it will be reversed. But the same principle applies. So let's have a look at the VDB, how VDB looks at this. Okay, and we're seeing exactly the same thing. So it kind of meshes out the edge between inside and the outside of the volume. This is one of the most common ways to visualize a vector field. In this case, it's a velocity field. I have a volume inside. I've applied a volume VOP, and inside of that volume VOP, I'm basically just based on the position of each voxel, I'm generating a noise and outputting that 3D noise into the velocity, the vel attribute, which is going to be a velocity, a vector field. Even though it's visualized, you can see it here in the viewport as density. In fact, when you slice you can apply a volume slice, which is really interesting. It allows you to cut through the volume. And then you can use a volume trail to kind of offset. Each one of these points is going to be offset based on the velocity fields that are in this volume. And you can see it like this. You can control the trail length, how long it's going to be. You can advect by, so you have several options here, but right now what I want you to see is these trails that you see here represent the direction of the vector field. You can, if you offset the slice, you'll see that it changes because we have a 3D vector field. Each voxel has a different, based on the noise, each voxel will have a different velocity vector, and this will generate this type of motion on particles and smoke and stuff like that. Essentially the same way as we saw for particles, where the particle's position is being calculated and updated on each step based on its velocity. On smoke and volumes, smoke simulations, fire simulations, what we'll see is we'll have the same type of phenomenon happen. The difference is that instead of actually advecting the position of the particle, we won't be advecting the position of the particle, but instead we'll be advecting the value of density from voxel to voxel, and that will seem as though the smoke is actually traveling through space, when in fact it's the values that are traveling through space, and then they are represented as more or less dense, and it seems to us that there is an actual smoke going through. But yeah, so this is the very basic principles of volumes. we're going to go through a series of simple exercises just to get you more familiar with the workflows of volumes inside Houdini.